So we've been talking about this derivative operator, and we came up with the Hermitian version of it. And now what I want to do is look at, well, what eigenvalues can we get out of this operator? So the easiest thing is to define it in terms of what we call a k-space. So this operator would operate on a vector k, returning a eigenvalue k in the k-space. So this is the eigenvalue, if you remember, and this is the eigenvector. So even though we're using a lot of k's, capital K, lowercase k, k in a bracket, then we're talking about different things. Capital K is the operator, the derivative operator, and k is the space that gives us the eigenvalue of lowercase k from it. We could project our k space onto our physical x space, our spatial space. So we could take the product of k with the operator k operating on it, and what we would get is the eigenvalue, which is just a number, and I can take that eigenvalue out front, and now I have this product of two bases, the x basis and the k basis. So what are we going to do with that? Well, a lot of times what we do is we would then look at the, if we integrate over another basis, maybe that'll teach us something about what's going on. So let's take this bracket and turn it into an integral where we now have x k operating on a k prime space. And so now we have a product of k prime. No, not k prime, sorry. Let's go back. So what we have instead, let's project it onto a different space, x prime. Now we have the product of x prime and k, and we now integrate over the x prime space. So we are essentially going to, integrate over x prime, because again, we think we know how to work with x prime. Say x prime is Cartesian coordinates, x is spherical coordinates, k is just this abstract thing we haven't figured out yet. But we know how to work with x and x prime. And so when we do that, what do we get? Well, we would follow the same rule they had before. K is the derivative operator. And so k would give us, this integral would give us minus I, the derivative with respect to x, because the delta function, k is a derivative of x, onto a function psi sub k as a function of x. And then that is now equal to our k eigenvalue times the function back again, right? Because that's what this is, x k. So the product of the x basis and the k basis. So now we have this written in functional form instead of bras and kets, that the derivative with respect to space of a function is the eigenvalue from k space times that function back again. Okay, so we're gonna, again, I keep using the term, this is actually, the psi is the classical wave function. Or it's the it's the regular use of the wave function, not classical mechanics, but it's the regular wave function we normally see. And so let's say, let me pick a nice wave function. So something that's periodic would be an amplitude times I, k, x. And we have to figure out what that a is. Well, to do that, we'd have to normalize it, which we'll do in a second. And remember that k is the eigenvalue, and e to the I k x is now something called an eigenfunction. So we had eigenvectors, and now so we're dealing with functions instead of vectors. It's an eigenfunction. Okay, what about that normalization? Well, later on, we'll find out how to normalize it, but I'm just going to tell you the answer right now. The answer is it's 1 over the square root of 2 pi. So our k space vector, or eigenvector, is 1 over the square root of 2 pi e to the I k x. Now let's look at the product of a k space and a k prime space. So in that case, I would be integrating from minus infinity to infinity of k over, let's say, an x space dx. What does that give us? Well, we worked out before that this is 1 over square root of 2 pi e to the I k prime x. And this, remember, take into account the complex conjugate, is 1 over the square root of 2 pi e to the minus I k x. So if I put those two things in, I would get 1 over 2 pi, so we got two of them to multiply together, the integral from minus infinity to infinity, e to the minus I k minus k prime times x dx. Okay, but remember, this is a basis. This is a product of two bases, k and k prime. And if they're orthogonal, then, or ortho, yeah, or if they're orthogonal, then we should get the Dirac delta function. And so that means that this thing now should be the Dirac delta function in k space. Right here. Okay. So in this case, we're dealing with k's that are real. It could be that the k numbers are actually complex, but for the moment, we're just going to hold on to them as if they are real. And because if they were complex, let's say k was equal to a k1, a real number, plus I times k2, so k1 and k2 are both real numbers. If I was to put that into my wave function, I would get a e to the I k1x e minus k2x. So the I and the I multiplied together give you minus 1. This function here is not periodic. It's an exponential decay. And so therefore, it's not going to disappear at when x is equal to minus infinity. If x is equal to minus infinity, then this function here goes to infinity. So it doesn't meet that condition that we like for wave functions, where the wave function has to go to 0 at the endpoint in order to have a nice probability. So what we have now is an example where, well, yes, the k eigenvalues can be complex. The physics tells us they really should be real numbers. And so that's often what's called a Hilbert space. So a Hilbert space is a space where these functions will normalize to 1. So our function, so the space has to be defined such that we can normalize our functions to, the Dirac delta function, or essentially 1. Okay. So, but the Hilbert space is a general space. It doesn't have to be a physical space, as in x, y, and z. The Hilbert space could be momentum. The Hilbert space could be wave number. The Hilbert space could be frequency. So, the Hilbert space is a general space where the physics is maintained. So you should start creating a quantum mechanics for yourself, which are non-Hilbert spaces, but then you'd have to make up the rules as to what works in a your non-Hilbert space quantum mechanics. So for right now, we're going to stick with the Hilbert space that we use because it satisfies the conditions of being physical. That it's what we observe. So the last thing I want to do is to now take a look at, well, if I'm talking about this K space, it's not a space that we would walk around in. It's a variable space. But I could write this down, this function, as the product of my K basis times my vector, which defines F, which I can then rewrite into a X space like so, which I can now rewrite, now that I've defined what this K basis is with its normalization, 1 over the square root of 2 pi e to the minus I kx f of x dx. So I've translated all the pieces. That becomes the function. This is that well, it's the how the X space projects onto the K space. But if you look back into some of your math, what you find is that this is something called the Fourier transform. And so really what we're doing is we're starting with a function in X space and turning it into a function in K space. And so we're able to, Fourier realized this, almost 100 years before quantum mechanics was developed, that, if I want to, I can translate between different variables, but what we call them spaces, because really it's variables that now are functions of those variables. And so we can jump between talking about a wave in its spatial, how it's spread out over space in X, and then we can Fourier transform that into something like its wavelength number. So this has a particular wavelength number, K. So it's a single value for the wavelength. But if I had a different wave, then I would get a wave number which is probably down here, because I now have a different number which quantifies the wavelength. And so this would be our function in terms of wavelength space. So I will stop here, and you can pick up on the next videos how we're going to come up with operators for X space and see how that works with the operators in K space.